Hello everyone! Today we'll have a new lesson about operating system, its processes, process scheduling, and scheduling algorithms. Let's talk about first the operating system processes. Process is basically a program in execution. The execution of a process must progress in a sequential fashion. A process is defined as an entity which represents the basic unit of work to be implemented in the system. To put it in simple terms, we write our computer programs in a text file, and when we execute this program, it becomes a process which performs all the tasks mentioned in the program. When a program is loaded into the memory and it becomes a process, it can be divided into four sections: stack, heap, text, and data. The following image shows a simplified layout of a process inside main memory. So there is the stack, heap, data, and text. Let's define or have the component and description of stack. The process stack contains the contemporary data such as method or function, parameters, return address, and local variables. Then the heap. This is dynamically allocated memory to a process during its runtime. Next is the text. This includes the current activity represented by the value of program counter and the contents of the processor's registers. And the data, wherein this section contains the global and static variables. How about the program? A program is a piece of code which may be a single line or millions of lines. A computer program is usually written by a computer programmer in a programming language. For example, here is a simple program written in C programming language. A computer program is a collection of instructions that performs a specific task when executed by a computer. When we compare a program with a process, we can conclude that a process is a dynamic instance of a computer program. A part of a computer program that performs a well-defined task is known as an algorithm. A collection of computer programs, libraries, and related data are referred to as software. The process life cycle. When a process executes, it passes through different states. These stages may differ in different operating systems, and the names of these states are also not standardized. In general, a process can have one of the following 5 states at a time. First is start. This is the initial state when a process is first started or created. Next is ready. The process is waiting to be assigned to a processor. Ready processes are waiting to have the processor allocated to them by the operating system so that they can run. Process may come into this state after start state or while running it but interrupted by the scheduler to assign CPU to some other process. Then followed by running. Once the process has been assigned to a processor by the OS scheduler, the process state is set to running and the processor executes its instructions. Then waiting. Process moves into the waiting state if it needs to wait for a resource, such as waiting for user input or waiting for a file to become available. And last is the terminated or exit. Once the process finishes its execution or it is terminated by the operating system, it is moved to the terminated state where it waits to be removed from main memory. So here is the start, ready, running, wait, and terminated state. Process Control Block or PCB. A process control block is a data structure maintained by the operating system for every process. The PCB is identified by an integer process ID or PID. A PCB keeps all the information needed to keep track of a process as listed below in the table. So here's the information and description. First, process state. The current state of the process, like whether it is ready, running, waiting, or whatever. Next is the process privileges. This is required to allow or disallow access to system resources, followed by process ID, wherein this is a unique identification for each of the processes in the operating system, and pointer, a pointer to parent process, then the program counter. Program counter is a pointer to the address of the next instruction to be executed for the process. Next is the CPU registers. Various CPU registers where process need to be stored for execution for running state. Next is the CPU schedule information, wherein process priority and other schedule information which is required to schedule the process. Then the memory management information, wherein this includes the information of page table, memory limits, segment table depending on memory used by the operating system. Next is the accounting information. This includes the amount of CPU used for process execution, time limits, execution ID, and so on. Then the input-output status information. This includes a list of input-output devices allocated to the process. So here is the architecture of a PCB is completely dependent on operating system and may contain different information in different operating systems. Here is a simplified diagram of a PCB. The PCB is maintained for a process throughout its lifetime and is deleted once the process terminates. Let's proceed to the operating system, which is the process scheduling. Process scheduling is the activity of the process manager that handles the removal of the running process from the CPU and the selection of another process on the basis of a particular strategy. Process scheduling is also an essential part of a multiprogramming operating systems. Such operating systems allow more than one process to be loaded into the executable memory at a time, and the loaded process shares the CPU using time multiplexing. The process scheduling queues. The OS maintains all PCBs in the process scheduling queues. The OS maintains a separate queue for each of the process states, and PCB of all processes in the same execution state are placed in the same queue. When the state of a process is changed, its PCB is unlinked from its current queue and moved to its new state queue. The operating system maintains the following important process scheduling queues, such as job queue. This queue keeps all the processes in the system. The ready queue. This queue keeps a set of all processes residing in main memory, ready and waiting to execute. A new process is always put in this queue. Then the device queues. The processes which are blocked due to unavailability of an input-output devices constitute this queue. The OS can use different policies to manage each queue: FIFO, round robin, priority, and so on. The OS scheduler determines how to move processes between the ready and run queues, which can only have one entry per processor core on the system. In the above diagram, it has been merged with the CPU. The two-state process model refers to running and non-running states, which are described below. So here are the state and description. First, the running. When a new process is created, it enters into the system as in the running state. Second is the not running. The processes that are not running are kept in queue, waiting for their turn to execute. Each entry in the queue is a pointer to a particular process. Queue is implemented by using linked lists. Use of dispatcher is as follows. When a process is interrupted, the process is transferred in the waiting queue. If the process has completed or aborted, the process is discarded. In either case, the dispatcher then selects a process from the queue to execute. What is schedulers? Schedulers are special system software which handle process scheduling in various ways. Their main task is to select the jobs to be submitted into the system and to decide which process to run. Schedulers are of three types: the long-term scheduler, short-term scheduler, and medium-term scheduler. Let us first define the long-term scheduler. It is also called the job scheduler. A long-term scheduler determines which programs are admitted to the system for processing. It selects processes from the queue and loads them into memory for execution. Process loads into the memory for CPU scheduling. The primary objective of the job scheduler is to provide a balanced mix of jobs such as input-output bound and processor bound. It also controls the degree of multiprogramming. If the degree of multiprogramming is stable, then the average rate of process creation must be equal to the average departure rate of processes leaving the system. On some systems, the long-term scheduler may not be available or minimal. Time-sharing operating systems have no long-term scheduler. When a process changes the state from new to ready, then there is use of long-term scheduler. Next is the short-term scheduler. It is also called a CPU scheduler. Its main objective is to increase system performance in accordance with the chosen set of criteria. It is the change of ready state to running state of the process. CPU scheduler selects a process among the processes that are ready to execute and allocates CPU to one of them. Short-term schedulers, also known as dispatchers, make the decision of which process to execute next. Short-term schedulers are faster than long-term schedulers. And last is the medium-term scheduler. Medium-term scheduling is a part of swapping. It removes the processes from the memory. It reduces the degree of multiprogramming. The medium-term scheduler is in charge of handling the swap-out processes. A running process may become suspended if it makes an input-output request. A suspended process cannot make any progress towards completion. In this condition, to remove the process from memory and make space for the other processes, the suspended process is moved to the secondary storage. This process is called swapping, and the process is said to be swapped out or rolled out. Swapping may be necessary to improve the process mix. So here is the sample comparison among scheduler between the long-term scheduler, short-term scheduler, and medium-term scheduler. In long-term scheduler, it is a job scheduler. Speed is lesser than short-term scheduler. It controls the degree of multiprogramming. It is almost absent or minimal in time-sharing system, and it selects processes from pool and loads them into memory for execution. While the short-term scheduler, it is a CPU scheduler. Speed is fastest among other two. It provides lesser control over degree of multiprogramming. It is also minimal in time-sharing system, and it selects those processes which are ready to execute. Then the medium-term scheduler, it is a process swapping scheduler. Speed is in between both short and long-term scheduler. It reduces the degree of multiprogramming. It is a part of time-sharing systems, and it can reintroduce the process into memory and execution can be continued. Let us define the context switch. A context switch is the mechanism to store and restore the state or context of a CPU in process control block so that the process execution can be resumed from the same point at a later time. Using this technique, a context switcher enables multiple processes to share a single CPU. Context switching is an essential part of a multitasking operating system features. When the scheduler switches the CPU from executing one process to execute another, the state from the current running process is stored in the process control block. After this, the state for the process to run next is loaded from its own PCB and used to set the PC, registers, and so on. At that point, the second process can start executing. So this is the example of the process. Context switches are computationally intensive since register and memory state must be saved and restored. To avoid the amount of context switching time, some hardware systems employ 2 or more sets of processor registers. When the process is switched, the following information is stored for later use. These are the program counter, scheduling information, base and limit register value, currently used register, change state, input-output state information, accounting information. Let's talk about the operating system in terms of scheduling algorithms. A process scheduler schedules different processes to be assigned to the CPU based on particular scheduling algorithms. So there are 6 popular process scheduling algorithms. These are first come first serve or FCFS scheduling, shortest job next or SJN scheduling, priority scheduling, shortest remaining time, round robin or RR scheduling, and multiple level queues scheduling. These algorithms are either non-preemptive or preemptive. Non-preemptive algorithms are designed so that once a process enters the running state, it cannot be preempted until it completes its allotted time. Whereas the preemptive scheduling is based on priority, where a scheduler may preempt a low priority running process anytime when a high priority process enters into a ready state. Let's talk about first come first serve or FCFS. Jobs are executed in first come first serve basis. It is a non-preemptive, preemptive scheduling algorithm. Easy to understand and implement. Its implementation based on FIFO queue or first in first out queue. Then for in performance as average wait time is high. So this is the example. Wait time of each process is as follows. So in process 0, there is the service time 0 minus the arrival time 0. Then the P1, service time 5 minus arrival time 1. P2, service time 8 minus arrival time 2. And P3, service time 16 minus arrival time 3. So the average wait time from 0 plus 4 plus 6 plus 13 divided by 4 is equals to 5.75. Then the shortest job next or SJN. This is also known as shortest job first or SJF. This is a non-preemptive, preemptive scheduling algorithm. Best approach to minimize waiting time and easy to implement in batch system where required CPU time is known in advance. Impossible to implement in interactive systems where required CPU time is not known and the processor should know in advance how much time process will take. So given the table of processes and their arrival time and execution time. Waiting time of each process is as follows. P0, the waiting time. So 0 minus 0. P1, 5 minus 1. P2, 14 minus 2. And P3, 8 minus 3. So the average wait time for the 0 plus 4 plus 12 plus 5 divided by 4 is equal to 5.25. Then the priority-based scheduling. Priority scheduling is a non-preemptive algorithm and one of the most common scheduling algorithms in batch systems. Each process is assigned a priority, process with highest priorities to be executed first, and so on. Processes with same priority are executed on first-come, first-served basis. Priority can be decided based on memory requirements, time requirements, or any other resource requirement. So, given the table of processes and their arrival time, execution time, and priority, here we are considering 1 is the lowest priority. Waiting time of each process is as follows. For P0, 0 minus 0. P1, 11 minus 1. P2, 14 minus 2. And P3, 5 minus 3. So for the average wait time of 0 plus 10 plus 12 plus 2 divided by 4 is equal to 6. Next is shortest remaining time. Shortest remaining time, or SRT, is the preemptive version of the SJN algorithm. The processor is allocated to the job closest to completion, but it can be preempted by the ready job with shorter time to completion. Impossible to implement in interactive system where required CPU time is not known, and it is often used in batch environments where short jobs need to give preference. Another scheduling algorithm is the round-robin scheduling. Round-robin is the preemptive process scheduling algorithm. Each process is provided a fixed time to execute. It is called a quantum. Once a process is executed for a given time period, it is preempted and other process executes for a given time period. Then the context switching is used to save states of preempted processes. So this is the example. For the waiting time of each process is as follows. So for P0, the wait time is 9. For P1, the wait time is 2. P2, the wait time is 12. And P3, the wait time is 11. So for the average wait time of 9 plus 2 plus 12 plus 11 divided by 4 is equal to 8.5. Next is the multi-level queue scheduling. Multiple level queues are not an independent scheduling algorithm. They mute queues of other existing algorithms to group and schedule jobs with common characteristics. Multiple queues are maintained for processes with common characteristics. Each queue can have its own scheduling algorithms, and priorities are assigned to each queue. For example, CPU-bound jobs can be scheduled in one queue and all input-output bound jobs in another queue. The process scheduler then alternately selects jobs from each queue and assigns them to the CPU based on the algorithm assigned to the queue. So that's all the discussions of operating system in terms of processes, process scheduling, and scheduling algorithms. Thank you for watching and have a nice day.